Yesterday, we learned how to take advantage of a matrix representation to conduct carbon cycle diagnostics. Today, we are going to learn another advantage from matrix approach, the semi-analytic spin-up. In this presentation, we will firstly talk about what is spin-up, why we need spin-up, and second, we will introduce current CLM spin-up approach and the existing issue. Then we will show you how semi-analytic spin-up is implemented in CLM5. This is a picture of Manhattan. I will try to use this example to illustrate what is a spin-up. Imagine all people in Manhattan leave the city for some reason and never come back. After years and years, what will happen? The nature power will work out. The city might change into a forest land. Ecological theory believes the succession will ultimately bring the ecosystem to a steady state, which means no matter whether it was a city or a cropland, it can ultimately change into a forest land without human activities. Spin-up, like such processes in regarding to model simulation, allow the system to grow by itself from any initial condition to a steady state. The question is, why do we need spin-up? Because spin-up provides an initial condition for model simulation. We know carbon dynamics can be formulated by this differential equation, since definite solution needs a boundary condition. In this case, we need an initial condition, especially when we simulate the land carbon uptake. The carbon balance in first few years will be very sensitive to the initial condition. If we conduct a global historical simulation, for example, from 1850, we need to know what was the global carbon storage in 1850. Unfortunately, we don't have such data. What we do is to make an assumption that before 1850, the carbon cycle is under the steady state. To achieve such steady state, we use a constant pre-industrial atmosphere CO2 concentration and also a recursive meteorological forcing to drive the model. Practically, we can see the model approach its steady state under the recursive forcing year by year. Model intercomparison projects greatly rely on spin-up to standardize the model initialization. In the protocol, standardized spin-up criterion are usually specifically written. For example, in MSTMIP protocol, steady state should be checked before transition simulations. 95% of grid cells should pass the equilibrium check. That ecosystem carbon stock change is less than 1 gram carbon per meter square per year. Community land model is one of the most famous landscape models developed by NCAR, with the largest user community around the world. Their criterion for spin-up includes changes in global carbon storage should be less than 0.02 gigaton carbon per year. The disequilibrium grid cell should be less than 3%. This criterion usually have the model to run over thousands of years. Spin-up usually represent most of the computational cost. Especially, more and more nonlinear processes such as the soil nitrogen computation are added into the model. Original spin-up method become hard to meet our needs. New spin-up approaches have been developed. There are now 3 methods for CLM5 to conduct their spin-up. The first one is the conventional one, the normal spin-up, to recursively use the meteorological forcing to drive the model year by year. The second one is the accelerated decomposition spin-up, which is initially developed by Peter and Thornton in 2005. Since the time cost for the spin-up is mostly contributed from the passive soil pools, The model can be accelerated by timing a spin-up factor, for example 10, to the passive soil turnover rate. Then run the model to the steady state. The steady state should be only 1/10 of what it should be because we have timed the spin-up factor. So we time the spin-up factor back to the carbon pool size and followed by the normal spin-up until steady state. The third one is our semi-analytic spin-up. Since we know carbon storage capacity in the tractor for the carbon storage, we just let the carbon storage equal to the carbon storage capacity, so carbon storage can approach steady state faster. The code has been well developed and tested by NCAR analysts. Now it is ready for them to absorb the code. There are some motivations for us to develop semi-analytic spin-up. Before semi-analytic spin-up, CLM5 uses the accelerated decomposition spin-up. We call it AD spin-up. As more and more carbon and nitrogen interaction is incorporated into the model, the efficiency becomes an issue for AD method. As we mentioned before, AD spin-up includes two phases, an AD spin-up phase and a normal spin-up phase. As you can see, after 200 years AD spin-up phase, total ecosystem carbon reached the steady state quickly. But the unbalanced grid cell decreases slowly, especially there are always more than 3% grid cells stay unbalanced after 1,500 years. Remember that our historical simulation only needs at most 300 years, so AD method also become expensive for some grid cells. So we start to think about whether an analytic solution exists for the carbon cycle model system. We found if we formulated the carbon dynamics into the matrix equation, the analytic solution should meet the second equation when dC over dt equals to 0. If B, I, A, C, and K are not related to pool size or time, which you call it linear autonomous system, the analytic solution can be easily expressed by the third equation, which is the carbon storage capacity. To calculate the carbon storage capacity, we need to rewrite the carbon flow into a matrix format. This is actually an exercise we have done yesterday. In CLM5 vegetation carbon cycle, there are totally 18 pools and changed by several major processes such as location, phenology, metallity, and fire. The nitrogen dynamics is all similar to the carbon, but adding the retranslocation pools. When old leaves are lost, part of the nitrogen will be transferred into the retranslocation pools and ready to reuse. In CLM5 below ground carbon cycle, 7 pools are included. Each pool contains 20 soil layers, so there are totally 140 compartments. Model considers 3 processes, such as amount pool transfers, vertical transfers, and fire. Carbon and nitrogen dynamics are similar. Matrix representation didn't change processes in the model, so results should be identical to the original model. We validated the matrix representation by comparing with the original model results. It's almost 100% identical. The maximum bias is only 1%. By assigning carbon storage capacity to the carbon storage as the last step of each forcing loop, we're able to do the semi-analytic spin-up. If the model is a linear autonomous system, the system should converge at a single solution immediately. The right figure illustrates why there can be 2 solutions. The red line represents the first term of the second equation, while the blue line represents the second term. The point there across represents the solution of the steady state, because the left-hand side of the equation should equal to 0 at the steady state. There is only one cross point, so there is only one solution. This is under the assumption of a linear model. However, the nonlinearity exists in the real model. For example, the leaf is a function of leaf carbon, which makes the system nonlinear. We assume the carbon input has an exponential relation with the leaf carbon, so the system will have two solutions, as the right figure shows. Fortunately, the solution x equal to 0 is a non-stable solution. When leaf carbon grows up, carbon input will grow accordingly and further help leaf carbon grow. The system will easily escape from the solution x equal to 0. However, when adding the nitrogen computation, we should find x equal to 0 become a conditional stable solution, because leaf carbon growth will use up soil mineral nitrogen and constrain the total carbon input. In this case, we need AD spin up to accelerate the soil nitrogen cycle, and also leaf carbon grow and escape from the x equal to 0 solution. So we recommend the SASU spin up should contain two phases as well, an AD phase and a semi-analytic spin up phase. If we have two phases for the semi-analytic spin-up, how long should we run AD phase before the semi-analytic spin-up phase? We conduct the sensitivity simulation, which the color lines represent that we run AD for from 40 to 200 years. Color lines almost overlap for both carbon storage and the unequilibrium grade cell, which means the timing to turn off the AD is not that critical. This is the criterion we showed before for CLM5 spin-up. Let's put this criterion on above simulations. These sensitivity simulations are all followed by a normal spin-up to test whether the spin-up will pass above criterion. We found earlier the AD phase shifts to the SASU phase, the longer the SASU phase will spend. Overall, in most cases, it takes about 400 to 440 years to reach the steady state. The fourth case has a less unequilibrium grids, so we take the fourth case as the standard approach. We compare the SASU method with the standard method in regarding to the consistency, the stability, and the efficiency. We compare how different their steady-state carbon storage are. We found in most grid cells, they have a similar amount of ecosystem carbon storage. There are several grid cells with a large discrepancy, which mostly located at high latitudes or dry regions. Soil carbon contribute most of the discrepancy. We guess both carbon input and turnover rate can be zero in those grid cells because both dry region and high latitude can have a zero water scalar. In this case, steady state can't be analytically solved. The initial value will remain unchanged through the whole simulation. Both AD and SASU in this case may not get a realistic answer. When we set those pools without any turnover to zero, the global total ecosystem carbon storage matches between two spin-up approaches. By comparing the stability of the two approaches, we found that the change in ecosystem carbon are small in both approaches. The unequilibrium grid cells represents 3.8% in standard approach, which is a little higher than the 2.7% in semi-analytic spin-up approach. Look at the efficiency. We also found the semi-analytic spin-up approach spent just 400 years, which is 73% faster than the standard approach.